Okay, so what we have here is our gravity well ready for action. Now what we're actually doing is we're simulating what we're calling a potential energy model. Now the way I would do it with students, and when we do it with year 10s, year 11s or even sixth formers, is that I try to explain first of all that the way we model potential energies is fundamentally linked in with forces. And so what we've got here is we've got a region where everything is at the same potential energy level. And I'm going to use this to represent an area of space in which there's no star, there's no planet, so there is effectively no gravity field. Now it's really important for this to keep your potential energy well completely level, because if it starts going up like this and going like this, it won't work. And this is where you just need to make that really clear to students right at the start. If we just drop this one down slightly. Okay, as a model, if we've got a region of space in which there's no gravity field at all, it means that anything going through this region of space will have no external forces acting on it. As we know from Newton's laws, if there's no external force acting on something, that object will either just sit completely stationary where it is, or whatever motion it's got, it will just keep going in a straight line forever. And we can see that that goes pretty much straight over. Do need to be careful with marbles getting dropped off here, and that's one of the reasons why we're going to be wearing goggles, because as we'll see when we bring the effects of gravity in, there is the potential, doesn't happen very often, for marbles to start flying around. It's only happened once or twice in my teaching career, but taking no chances, I always get the students to wear goggles when we're doing this. If, having had a region of space which something's going through, there's no gravity field, we've seen that an object will move pretty much in a straight line. This is just a model, and it's got its limitations. I mean, let's face it, it's just lycra and it's just a hula hoop, so we might get a slight deviation there. Of course, we've got friction with the lycra surface, which we wouldn't have in space, but it's still a pretty good analogy that the students can work with. What we're now going to do is we're going to represent what would happen in gravity terms if we have a huge clump of mass in this region of space, something like a star. So what Kieran is going to do is in the centre of the gravity well, he's going to pinch down and he's going to pull it down quite a long way. What this is effectively doing, if we think about this in potential energy terms, is he's creating a potential energy well. Another way of looking at this, it's possible to show mathematically that the slope of this potential energy well will give us a measure of how strong the gravitational field is within this region. Now either way, as far as a marble is concerned, it doesn't care whether we're thinking of potential energy or we're thinking of forces. The effect on the marble's path, Kieran, can you pull down a little bit more please? The effect on the marble's path is that it no longer goes in a straight line. Instead, we get an orbital path, and one of the key things that we can see here is that that orbit is not circular. In fact, there is no such thing as a circular orbit when it comes down to one object orbiting another, because they actually exert forces on each other, and what we get are these elliptical orbits. And there's all sorts of properties that we can explore here. We can get orbits that are nearly circular. We can get orbits like comets, which are highly elliptical. And we can see other phenomena as well, that as a marble gets closer to the source of the gravitational field, the gravitational force itself gets stronger, and so the comet comes barreling in towards the inner solar system and then slows down as it gets further out. Not only can we show the effect of one planet in a solar system, but if I get another marble, and I just stop this one here, we can actually show very clearly, so if we just make this level again, we can show very clearly that very slight differences in the paths of two objects can result in radically different orbits. So I'm going to launch these two marbles together, and what we should see is that from start velocities that are only slightly different, we have got orbits that are starting to be quite different in their behaviour. Now you can extend this as far as you like with 3 or 4 planets, but one of the really interesting things that you can do is that when we look out in the galaxy, most stars are not on their own. They exist in pairs or in triples, and we call those binary or triple star systems. Now if we want to show the gravity field of a binary star system, Kieran, you're going to need both your hands for this. Could you now pull down 2 little dimples please? And we can have another one over here.
Do you want me to do that one?
Okay. What I generally tend to do with students is maybe to have 4 of them holding and then somebody else down here. Now if we bring these up slightly so that we've got low mass stars, okay, we're going to have relatively weak gravitational fields, but now we still get orbital paths that are quite unusual, and we have got occasionally objects that suddenly seem to move backwards. Believe it or not, we do see these type of dynamics in the real solar system. Of course, if we have one partner that is much more massive than another, so Sarah, can you pull that one down radically? Kieran, can you let this one come up? Then obviously the dominant effect is going to be from this gravitational source. And so it is as if, and this one has just deflected through here and gone straight in here, it is as if the entire solar system here is dominated by this mass, and this is just having a tiny effect which will manifest itself if something comes through here. So if I launch this through here, we can see it's pretty much this field that will dominate. Out in a distance though, we've got the horseshoe coming through there. And as we say, especially with small objects orbiting big planets, we do start to see these effects coming into play in the real solar system. One really important point here, if I could now replace this, Sarah, can we just do a single gravitational field source? If we go at a high enough velocity, and you need to be careful about this, then the object will not have an orbital velocity, but it will have what we call a hyperbolic escape velocity, and it will go shooting out of the solar system and off the surface of your gravity well. So you just need to watch out for this. That wasn't quite big enough. Neither was that, but there'll always be some pupil who'll go, whoa, what's going to happen when I do this, sir? It goes wallop and it goes phew, and it goes flying. But once again, if we want to launch a spacecraft to go out of the solar system and never come back, it is possible. A number of spacecraft have done this. We just need to give it more than the velocity it needs to make an orbital path, and we call that solar system escape velocity. The final point, gravity, as far as we're modelling it at school, is an attractive force, which means we're pulling downwards with this. There is some evidence that is coming out now more and more that on the large scale structure of the universe, we're not sure if it's gravity or some other unknown force, but there seems to be a repulsive effect that only manifests itself on huge scales when we think of the distance between galaxies. In other words, even gravity itself, when it comes down to the large-scale structure of the universe, it's still not fully understood. Of the 4 fundamental forces in nature, it is gravity that is the most mysterious one. If gravity were repulsive, though, instead of pulling downwards, of course, we would have the gravity well going upwards. And so the gravity well itself, what I tend to do with students is have clear foci on what I want them to work on. It might be what happens, again, Sarah, if I can ask you to pull this down, you know, what happens to the velocity when you get closer to the source of the field, and the students can see very clearly that the velocity vector itself gets larger, and that makes sense because the closer you are to a source of gravity, the higher the force is itself. So all sorts of possibilities that we have using this setup.